Hi guys, this morning we have a thing you can play with right now. So this is a Hugging Face Spaces SplatWorld. Actually, I had to delete some old Hugging Face Spaces because you get to there's a space limit there these days and how many things you can have. But well, that doesn't matter. Nobody's looking at my Hugging Face Spaces. But so this is now live. And what I did overnight was I trained on the celeb dataset and we made tiny, even smaller than before, 7 megabyte web interference field. So we are using splats, and what this thing is basically, we have this splat space where we can zoom, like I can show you guys. So there's two apps actually. There's one app it runs on your computer using the Kinter graphic user interface, and one is this. And this is kind of shitty because it's running on CPU at Hugging Face. But so, like here, you guys can see it's zooming into the space, and as you guys see, there are these very odd changes. So it's a frequency space. It's a frequency space where these things are kind of stand-ins for neurons, and it goes through like kind of like whatever it saw as faces. The training, you guys could train on this anything. The initial version was trained on flowers, so whatever data set you want, you can put the flower. You can just, I think the how you train is somewhere here. So there's the train your own model. So here is kind of how you train. The important thing is that you use low beta. If you don't use low beta, what happens is that you start to get a posterior model collapse, which means that all of the stuff is just gray. Like either it collapses to a one face or all of it collapses to a gray. But like what you guys can see here after 30,000 epochs, it kind of can do different faces. And this is actually what we are exploring. And the mind-blowing thing, the reason why the model is at GitHub, because it is 7 megabytes, splatdecoder.the ONNX. If you use the trainer here, a thing to remember is that you have to turn it into a ONNX compatible thing, and I'm just looking at let's see, where was the trainer bits here. So you actually have to export. You have to do the export because it initially turns it into a PT file, which is normal model, but we are using ONNX, which is faster because I was messing with OpenCV5 here. But so I'm gonna show you guys in a bit like so we have two tools. We have the Hugging Face, which you can use right now, and we have the Explore Desktop that works way faster and does this sort of stuff live endlessly. But so what is interesting here? I mean, the space that we have these really weird, these gabor splats turning into faces. What does it mean? Like I was like initially like, why do we have this space between? Things I learned while doing this is that weird space between that already in the 90s they were doing face models where basically they were using kind of like how things move between kind of like simple faces, and they were doing something called linear transfer functions. And they were able to kind of like, if you map all of the spaces between the faces, you can kind of like start to make faces by just doing mathematics. But so these are the splats, and I don't know, do floaters have anything to do with them? But I have, like I call these floaters, but they are splats. And of course, the Gaussian splatting from back in the day was using splats and doing it in 3 dimensions, and this is whole field of things called there's nerf where you can do 3-dimensional models and all that. And why do this, and why do it again and again and again and again, and why be, well, I'm autistic. But so anyway, brain damage more like. But anyway, so the tiny model, 7 megabytes, my god. I mean, that's when I was a kid, we had 1.4 megabyte disks. already, I think, late 80s, early 90s, to think that this thing, the model would fit in 5 of those disks. Of course, we would not have the computer to run it. But I'm going to show you guys the Explorer desktop with ScanFo is really fascinating because it does that live endlessly. The model is tiny, like the images were trained on only 96 to 96. You can actually make it larger, but with my 12 gigabyte Radeon 306 so graphics card, I started to get out of memory errors, so I couldn't use that. So, so this is the Explorer desktop where you guys can see this endlessly, and this is mind-blowing to me. We see it's going to a splat. After that, it goes to another one, and you guys can see those spaces between the. So we are exploring the model's frequency space, and in the frequency space there are these splats, and when we zoom into one, it finds something else and whatever, and really cool. One weird thing that I have not spoken of this with any AI yet is why does it do the twist? It's slowly twisting, like it's gonna do actually a circle in the end. Very, 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 very complex thoughts by Fable, and well, Fable was pretty much running the show here. One weird ass thing we had like at one point, which was that basically when I was doing the model training was that all of the when it was trying to match faces from the training set. Let's see, do I still have it? All of the eyebrows were like this, and that was something that it's trying to match really hard. Like here, you guys can see all of the eyebrows were downward. But then we did some extra hyper, super duper complex things where we were using quantum mechanics. We somehow got the thing that the eyebrows are level. So, but just look at that. Just look at those splats moving. On the this desktop app, you also have a surf, which you also had on the Hugging Face thing, where you can do this and you can actually move through the space. Of course, we had the live code, which I should put where you can query it with your face. I should put that in there too. And here we have also the dive. We can do this, but so this doesn't actually have the webcam. But here we can move in this flat space, and you guys can, when you zoom in, they're all default. When we go out, they start to get back into the face-like. And if they look like celebrities, this is a Celebat dataset, which is free for non-commercial use. And well, I ain't gonna make any money out of this. But it's just utterly fascinating. It's utterly fascinating. And if you guys see these sorts of things in your vision sometime, well, it makes sense because occipital lobe uses this gabor space, gabor filtering frequencies, and very, very fascinating stuff. Somebody might say creepy, but there's someone with brain damage. Well, I have seen this sort of stuff in my vision, so kind of like, okay, yeah. Does make me feel a machine-like, but perhaps that's what we are, kind of. But yeah, so I'll link to this stuff, and at the end of this, right now, you guys will hear the technical explanation of what is happening here. I hope you guys are well. Bye.
Hey everyone, let's dive right into today's explainer. We're looking at a wildly fascinating GitHub project by Antti Luod called SplatWorld, and I gotta tell you, it completely rethinks how AI stores and generates images. If you're used to thinking about digital images as just a basic grid of colored squares, well, prepare to have your mind blown. We are talking about a system that generates highly detailed images while completely abandoning the very concept of the pixel. I want you to hold this massive number in your head for just a second. 202,599. That is the number of high-definition celebrity faces we are talking about today from the famous Celeb A dataset. Normally, storing or even just learning the features of this many faces requires massive neural networks, gigabytes of data, and some serious computational power. But SplatWorld does something almost unbelievable with this massive population. Now, here is a literally mind-bending claim straight from the project's creator. they managed to cram an entire population's worth of faces into a single file smaller than an MP3, just 7.2 megabytes. That is the whole shebang. And it accomplishes this using absolutely 0 pixels. There's no traditional image grid hiding in this code. It's doing something entirely different to bring these faces to life. So how exactly does this magic trick work? Well, our roadmap for today is pretty straightforward. We'll look at generating faces without pixels, drawing with wave interference, the chaotic fire between faces, the transport problem, and finally, how you can enter SplatWorld yourself. All right, kicking things off with section 1, faces without any pixels. Let's demystify this 7.2 megabyte illusion. You know how standard AI image generators usually rely on heavy, complex, convolutional neural networks to paint images pixel by pixel? Well, SplatWorld throws that out the window. Instead, it uses a tiny variational autoencoder, or VAE. It simply maps a 128-dimensional coordinate, which we call Z, to just 256 individual packets. There are absolutely no convolutions happening here. It doesn't store pixels, it doesn't paint pixels, it just outputs these 256 packets of math. So the absolutely crucial thing to understand here is the gabor wave packet. You can think of a gabor wave packet as a mathematical atom. Each one carries specific instructions: where to be, how big to be, what direction to face, and how fast to vibrate. It's basically the math equivalent of a vibrating drumhead. And here is the kicker. 256 of these vibrating mathematical drumheads are all we need to build a completely recognizable human face. Crazy, right? Moving right along to section 2, drawing with wave interference. Let's see how this math actually creates an image. The AI isn't holding a paintbrush. The renderer simply drops all 256 of those vibrating atoms onto a blank 96 by 96 canvas and just adds their ripples together. It's that simple. Where the peaks of the waves meet, they amplify. Where a peak meets a trough, they cancel each other out. So a face in this system is nothing more than a phase-locked standing wave. It's this perfect symphony of ripples mathematically aligning to form a sharp eyebrow or a soft cheekbone. What's even cooler is that we can literally watch the AI learn to do this during its training. It's a fascinating two-step dance. First, the envelope commits. The AI figures out the raw mass and amplitude of the face, which honestly just looks like flat, fuzzy, horizontal blobs. But then, step 2 kicks in. The carrier commits. The orientation and phase lock into place, and suddenly those fuzzy blobs snap into sharp, crisp facial lines. It gets the mass first and the sharp details second. Which brings us to section 3, the fire between faces. Sounds a bit like a glitch in the matrix, doesn't it? There are 2 totally different zones in this mathematical universe. Side A is the core. This is the safe zone where the AI has been trained. The peaks and troughs lock perfectly and you get a stable face. But if you push the coordinates out of bounds to side B, you enter the fire. Because there's no training data out there, the decoder just stops orchestrating the waves. The packets lose their sync, they wander, their phases drift, and they just beat against each other in this chaotic, messy soup of interference. The whole illusion just breaks down. Okay, section 4, the problem with transport, or as I like to call it, the ghost of 1990s tech. Why does this chaotic fire happen when we try to smoothly morph one face into another? Here's the core issue. Because this is a fixed additive model, if the AI wants to move an eyebrow from a little lower on the face to a little higher up, it can't actually just move it. It has to awkwardly crossfade them. It fades the old one out while fading a new one in, creating this fighting double exposure. That fire we just talked about, it is literally just this fight, this double exposure failure made completely visible as a wave interference glitch. This double exposure problem isn't actually new either. It's a ghost from 1991 when a tech called eigenfaces used linear combinations to build faces. SplatWorld is essentially just perfectly visualizing this old failure mode for us today. But look at the future direction on the horizon: phase transport. By leveraging the Fourier shift theorem, future models could actually slide features around smoothly just by rotating their mathematical phase. They could move the wave without ever destroying it. The creator also points out this crazy tug-of-war during training, all centered around a parameter called beta. If you use low beta, the faces are pushed apart. You get super crisp, distinct identities, but vast, terrifying oceans of that fire between them. If you crank the beta up to high, you squeeze the faces together. You get buttery, smooth morphs, and the fire disappears. But the massive catch is that all those distinct identities melt into one generic, bland face. Achieving density without collapse is a huge open problem here. All right, section 5. How to enter SplatWorld for some hands-on exploration yourself? The repository generously provides 4 distinct tools depending on your hardware. If you just want to mess around in your browser, app.py runs on Hugging Face and lets you surf with sliders. For a richer local experience, explore-desktop.py gives you real mouse drag surfing. If you want to bake thousands of thumbnails to map the whole space, use splatAtlas.py. And if you're feeling incredibly ambitious and have a CUDA GPU, SplatTrainer2.py lets you fire up a PyTorch environment to train this model entirely from scratch. I absolutely love the creator's commitment to an honest ledger here, transparently laying out the limitations. That 96 by 96 resolution, it's a strict hardware memory constraint, not some retro aesthetic choice. Hair and fine details are inherently going to struggle with this method. The faces you sample will heavily skew toward a generic mean. And when you are surfing, remember, you're only exploring a tiny 2-dimensional slice of a massive 128-dimensional universe at any one time. As we wrap up today's explainer, I want to leave you with this thought. We've seen how pushing a facial feature from point A to point B creates a glitchy, chaotic fire. But what happens when the next iteration of this model learns the loophole? What happens when AI perfectly masters face transport, smoothly sliding these waves across the canvas without ever breaking the illusion? The artistic frontiers that could open up are going to be absolutely staggering. Thanks for joining me today, and keep exploring.